After weeks of manufacturing delays, we finally had all of our parts. 7 months ago, 5 of us met as a group for the first time. The task was turning a simple problem statement into a fully functional prototype. This had to be tested on a test fixture, backed up with finite element analysis, failure mode effects analysis, and multiple other deliverables for the course.
My name is Chris Connor, Principal Engineer for Wind Turbines here at Northern Power. We are an energy storage and wind power company. We make a 100 kilowatt, 60 kilowatt wind turbine platform for the distributed wind market, and we're looking for some help in refining our yaw brake design for use on that platform.
My name is Ryan Connor. I'm a mechanical engineer.
Hi, I'm Richard Donito, mechanical engineer.
I'm Adam Grill. I'm a mechanical engineer.
My name is Phil Lamberton, and I'm a mechanical engineer.
I'm Chuck Norton. I'm a mechanical engineer.
Wind turbines yaw to keep themselves oriented into the wind. The wind is obviously unsteady, and the wind turbine needs to adjust to the optimal position for maximum energy harvesting. The reason why wind turbines need yaw brakes is to protect the yaw drive and motor from a phenomenon known as dithering, which is a transmission of uneven loading all the way out from the tips of the turbine blades to the interface between the nacelle, which is the top of the tower, and the tower itself. Yaw brakes protect these components by clamping down to lock in the lash between those gears.
For our design, our requirements were primarily that we needed to lessen any tangential movements of the brake pads. Tangential movement of the brake pads leads to knocking. Knocking is considered a nuisance noise.
Some of their brakes had that issue where after a while they would start to squeak like car brakes, and they wanted to see if a caliper system would maybe alleviate that noise.
So our design went through several iterations. Most of these were for ease of manufacturing. We started with a design that had radial edges. This was not feasible for manufacturing as it's hard to fixture within a CNC machine. So to combat that, we moved to a squared off side so that theoretically it could be grabbed easier. With these changes, we still were not able to manufacture it easily and cost effectively. So we moved to a 3-piece design.
Our design is slightly novel in the fact that it is a passive system, meaning that it's constantly engaged using tensioning of spring stacks, and the yaw drive and motor just overcome the friction of the pads to oscillate in the wind.
We went from doing a full disc segment, and then we needed to basically do a third of a piece of a brake disc, and so that would have been really complicated for us to do, and we hadn't found a machine shop to do it for us. So that was really where the machine shop saved us, is that it was able to cut it out from 1/2-inch Blanchard ground steel in a matter of 20 minutes. So where it would have taken us probably hours to try to cut up pieces and try to weld together and then ground that all down, it was able to do it in just a fraction of the time.
One way that we were able to cut costs with our budgets was actually having our team manufacture most of the custom parts. We estimate that this would have saved us somewhere between $1,000 and $2,000.
It was great to be able to use the new water jet in the UVM machine shop, but we still had to use some of the other tools to manufacture our parts. We lathed the ply plugs, we cut Delrin on the vertical and horizontal bandsaws, and we cut steel on the horizontal and vertical bandsaws to complete the Delrin end blocks, as well as the initial backing plate.
So a day after we got back the pieces from IMF, we went down to NPS, and that was basically our first day that we are going to be doing assembly proof and making sure that everything fit in the test fixture. So we definitely had our fingers crossed to make sure everything was going to fit, because it's one thing to model it up in SolidWorks and have SolidWorks tell you that it's going to fit. It's another to make sure that once you actually have manufactured parts, to ensure it's going to fit into a physical test fixture. So I definitely feel like everyone was pretty nervous about that. It was definitely a pretty stressful and trying time, but luckily everything fit in perfectly. So brake disc mount up beautifully, have everything fit in together, not very major issues with things. This is our, 8 months worth of work, actually having a physical prototype right there in front of you, and then first time going into the test fixture. That was just a really cool aspect.
So during testing and the assembly of the brake caliper, we ran into several issues of binding of both screws and of the plugs within the spring stack. There wasn't any severe binding, but there was some slight binding that didn't allow us to tension the bolts in the spring stack exactly to what we had specified. We fixed this by lubricating both the Belvo washers and the apply plugs. We were able to cut the torque we applied to them almost in half. We also found that we were able to consistently apply the same force to each bolt when they were lubricated. So one of the main factors with our testing was doing the brake bedding. Brake bedding is ensuring that you have an even pad surface on your brake pads, and that's essential so that you have a high contact pressure area. Before bedding, you have high spots, which leads to local areas of high pressure, and that does contribute to noise, one of the main issues with their previous designs. So during our testing, we put 6 hours of testing of Yang. 3.5 of those were bedding.
We used a static pull test to check the static torque of our brake. This was using a come-along winch to a I-beam and pretty much setting an equal torque between the distance of the come-along from tower axis and the distance of the brake to the tower axis. We were able to back out the torque that the brake was being applied and therefore confirm our pad coefficient of friction.
With this test, we were also able to determine that the braking torque was 3,700 kilonewton meters, which was 700 above our requirement. We also found that our pad backing translation was only 0.1 millimeters, which met our requirement perfectly. 0.1 millimeters is about the width of a human hair.
With this 3-piece design, it did result in a very high weight, which would probably be impractical for service personnel installing this caliper up in a nacelle of a wind turbine. So for future recommendations, we recommend casting for our caliper design. This would allow us to move closer to our original design in terms of geometry. It would cut weight by almost 50%. It also allow for simpler and more cost-effective manufacturing.
When we started out the project, NPS originally estimated that our project would cost $4,000. Throughout the last year, we found that we were able to create a prototype for them for approximately $3,500. Our testing found, even though we were only able to run for approximately 6.5 hours, we had no squealing and no knocking. Our service interval could be up to, if not over, 2 years, thus doubling the service interval of their current design. It's our recommendation that NPS runs our system for the full life cycle test to ensure our analyses were correct on our product.
It can't be overstated how much C Team 8 appreciates the time and mentorship put in by Chris Connor and Nick Seifert. It was a joy and an honor to work with them.
Ultimately, to see it work, hit all our requirements and all our metrics, that's probably one of the best feelings you can get as an engineer.